managed to drag me off. So as lunch is next, I'm probably not going to try and overrun at all, if anything. Yeah, I'll try and pretty much motor through this. So hi, I'm Bob. I'm a principal engineer at the BBC, and I work in the frameworks team. We are a team of 6 people, and we look after PHP, Apache, Varnish. We look after Zend Framework. Then we have a framework stuck on top of that, which we call the PAL, which is the page assembly layer. Then we also have on top of that a further framework called BBC Micro. Then we have a templating language called Spectrum. Then we're also responsible for the global and header and footer for the BBC, which is called Barlesque. We also look after jQuery, and the list goes on. We also look after a Java service layer, which I'll come into in a few moments. So the BBC runs on LAMP, but without the M. We don't have any access directly from PHP to any data layers. We have to go through a Tomcat service layer. I've mentioned Zend Framework already and the rest of it. So how does the BBC work? We have one domain. We are a shared platform. We kind of do have a bit more than one domain, but generally everything is served off www.bbc.co.uk. We have 2 technology stacks. We have the PAL layer, which is the PHP layer that I talked about. Then we also have some proxy passes, that go back to our legacy technology stack, but everything is moving off that and onto the PAL. All our data transfer internally is done with certificates, so client certificates talking to SSL endpoints. Proxy passes I mentioned. So we have about 360 different apps that run on www.bbc.co.uk. So iPlayer is 4. So we have iPlayer Desktop, which is just /iPlayer. We also have iPlayer for the TV. We have iPlayer for the TV version 2, which is the older. Version 2 is actually the older version. We also have iPlayer for the mobile. So if you add all of those up for CBBC, for sport, for weather, there's about 360, and they're all sat on the same servers. We had, at Christmas, we had 42 PHP servers running the whole of the BBC. So that's not a lot, considering we do about 30 million unique users a day, doing about 500 million page impressions. So we run quite a tight ship, and everybody's running on the same platform, so it's a shared host. So a surge on BBC Weather can take down iPlayer and anybody and the homepage and everybody else. So we're very careful about performance where we have to be. So a little bit more about our network topology. We have 2 data centers at the minute. We have one in Watford with the cleverly named WTF data center, and then we have London Telly West House, I think it is as well. We don't run any data center affinity, so your requests could be served out of either. Well, there is one caveat. There are a couple of apps that do have data center affinity, but we don't like to talk about them because we're trying to get them to stop it. This is roughly what our network looks like, but I've got a simpler version. So basically, all the traffic that comes into the BBC goes through one of several traffic routing patterns. We either go from the ZXTMs, which is our traffic routing servers, that's Zeus traffic managers, whatever, if anyone doesn't know what they are. They go straight to our page assembly layer, which is our PHP layer, and we serve content straight from there. So at the minute we have iPlayer, weather, BBC homepage. There's about 6 or 7 applications that are going through Varnish. So they go from our ZXTM into Varnish, then they go out of Varnish back to a ZXTM, and then onto our PAL servers again. And if our PAL ever tries to access any data, so if we want to talk to our programs information data services, or if we want to talk to our identity services, they hit yet another ZXTM that goes onto to the service layer, and we've actually started putting Varnish between that as well. So the most common scenario is for Dynamite, which is our programs data. That generates huge XML responses in the order of 1, maybe 2 meg. And previously they were going straight through a ZXTM. ZXTM only has about 2 gigabytes of cache, and it would expire it even though we were sending headers back that said it could be cached for an hour or 2 hours. Generally it was only cached for about 5 minutes. So Varnish has got 64 gigabytes of cache in there. So it's got plenty of room to store that, so we get a lot better cache hit ratio. So this is roughly what happens when you... so the ZXTMs are generally the same ZXTMs that you hit at the front end, and we do loop back, and same as the Varnish instances are actually the same Varnishes. So we're basically doing lots of loops around. And then we have... we do the routing in the ZXTM based on headers that are sent from Varnish. So when you come into the ZXTM at the top, that will set a header saying this is a request to a PAL box, and then when it comes out of Varnish, the ZXTM will then route it to the correct location. So I was going to talk a little bit about caching, because without our caching, we really wouldn't be able to serve on the 40-odd servers that we have. We now have about 70 servers as of just after Christmas, and that's mainly because we're scaling up to serve all the traffic for the Olympics. So the caching that we previously had was mod cache sitting in Apache. That was quite often defeated by Barlesque, which is our global header and footer, because that used to render different versions based on whether you were inside or outside of the UK, which meant that we couldn't cache it. Therefore, everything was sent as cache control private, which so every time you could still cache inside mod cache occasionally, but generally everything else was cache control private. So we were still hitting Apache for pretty much every request. So the reason that Barlesque changes that behavior is because if you hit a BBC property from outside the UK, you'll get served an advert. And you may well get redirected to bbc.com, which is worldwide our commercial arm. So to try and get some better caching out of that, we used another Apache module called mod annotate. And what this would do is when you hit, in fact, I'll go on and come back. So when you hit Apache with your request, mod annotate would hit 2 data services. It could hit more, but generally it hit 2. One which was a GIP service, a Java service layer, which is Quova, which I think was mentioned in one of the talks yesterday. And it also hits a service called Wurfel. Well, we call it Wurfel Demi, but it's the open source Wurfel, which is device metadata. That adds some headers onto the request. Generally, we roll up the IP info to just 2 headers. One which is, are you inside the UK, yes or no, and what type of device you are. Sorry, for the GYP, it's whether you're inside the UK and whether we should serve adverts to you. Because you could still be outside the UK, but we're not confident enough about your IP to actually show you adverts, so there's a compromise in there. The Wurfel dataset returns whether you're a desktop, a mobile, a television, a tablet PC. It also returns some metadata about whether your input type is touch, keyboard, mouse, scroll wheel, and all sorts of things like that. That allows our PHP applications to then send a vary back to say, I vary on whether I'm inside or outside the UK to change the header and footer. And I also have 4 different versions to say whether it's a desktop version, a mobile version, or a TV version. Particularly iPlayer use that a lot. We would get virtually no caching on iPlayer without that. because they serve up, they actually do slightly more. The Wurfel also returns a make and model of the television. We spend quite a lot of time modifying Wurfel to get manufacturer details for Samsung and LG televisions and things. Every once a month, we add about 7 or 8 new televisions to that. And then the iPlayer team decide whether you get version 4 or version 2, which is the old one. So yeah, that goes then into mod cache, and then because mod cache knows that the application varies on GeoIP and on the device type, it can actually cache it, and rather than invoke PHP, it will just return it straight out of disk cache, and then that gets sent back to the response. So this is what we used to do. We found that you're still hitting Apache and you're still incurring all the network latency and everything else. And we had some, it's not very easy to reconfigure mod cache. It's literally a straight HTTP RFC compliant HTTP cache. And we wanted to do something a bit more special with it. So we introduced Varnish. So Varnish was originally brought in to serve iPlayer content because they wanted to route for the televisions and mobile devices. And Varnish has a configuration language called VCL, which quite handily you can drop down to C, and you can embed your own libraries and your own C code within Varnish. So typical things we do in there is we normalize headers, we normalize accept encoding, we normalize quite a few things. We strip out some cookies. So the other thing is if you hit a BBC website, so this is the other thing that mod cache fell down on. If you hit a BBC website, the first time you hit it, if you don't have a cookie that's called BBC UID, we issue a set cookie back to set you a random cookie. I'm not entirely sure what it's used for, but it's actually an extension into Apache to set this cookie, and it kind of defeats caching quite a lot because a set cookie becomes a private, cache control private, no cache request. So we've actually moved this logic into our Varnish layer. So Varnish will, rather than hit the back end to go get them some content, it will return that from cache, and it will then modify the response to set the cookie and set the cache control to private again, so upstream caches don't cache it. We strip out cookies from stuff that really don't need to have cookies. And we also have a problem, a huge problem, with people using cache busters. We discovered last week or 2 weeks ago that we were actually only doing this for the iPlayer. I think parts of the iPlayer site will have a polling mechanism for now and next. And because of problems in IE 6, 7, 8, and probably every other version, if you use an AJAX request to go fetch some JSON, even though you tell in the response from the server cache control no cache, IE aggressively caches that, and the fix that everyone seems to do is append a random number on the end. So we strip that out in our Varnish layer so that we don't actually hit the back end, because we know that we can cache it for 10 seconds, but the clients want to go and refresh it. So that saved us quite a lot of load. And we discovered that when Sport pushed a new release of their, it was the cricket, the test match, started a couple of weeks ago, and the Sport site on their homepage had a little ticker that got the latest cricket scores. And they had a cache buster URL on the end of it, and that generated 15,000 requests per second to our back end. So we now implement this cache buster stripping on every request. The other thing we can do with Varnish, which is quite nice, is ESIs, which is edge side includes. So we can render the main page, which has your customization on it that says, "Hi Bob," but then things like the weather is specific to London, so everyone in London can get that, and what's now and next is specific to everyone in the UK. So we stick some tags in the page that says the page itself is not cacheable at all, but these little sections of the page are cacheable for 30 seconds, or the weather is cacheable for an hour or so. And the Varnish layer will go and fetch the page itself, but then it will push in all the content from weather and things like that, and it will serve it out, and it will assemble the page in the cache and serve it out. So you're only serving the bits of the page that need to be served. Everything else is still served from the cache. And whereas normally, so if Varnish disappeared, what happens in this situation is we have to go and fetch that data for every single person, assemble the page in PHP, and push it out, and it then becomes private because it's customized to me. Whereas this, we can customize only the bits of the page that need to be customized. Everything else is cached. Again, we do the GeoIP data and we do the device data inside Varnish. And what that looks like is, so this is a normal request hitting BBC iPlayer. And so the top one is your request from the browser. The bottom one is the response from the server. We're saying it's cacheable for 30 seconds. The user agent is whatever. We have the accept type and we have accept encoding. So if in a normal cache, if your accept encoding was deflate first and then gzip, you had two different variations of your page in your cache. So we normalize that, and I think we check for gzip first. If you support gzip, you get gzip. If you don't support gzip, but you support deflate, you get deflate. I think those are really the only two things we do, and that's your normal response. If you're then going through Varnish, what you will see is what the PHP server sees. We get the normal user agent information as before, but now we have this device was actually a desktop. It was actually in the country UK, so it is UK combined. So Northern Ireland, Scotland, Wales, all the rest of it are termed to be UK combined. I think there might be some overseas territories that also get UK combined. And then we tell it that we don't want to serve adverts to this page. Oh, sorry. And then in the response, the server is now told the cache, which is Varnish in this case, that I'm going to vary on the device type and is UK combined. So basically I have a international version and I have a domestic version, and I'm varying on whether it's a mobile device or whether it's a desktop. So that will also create different versions in the cache. So we'll have two copies for is UK combined, so we'll have the two copies for internal, domestic and international, and then we'll have up to 4 copies. So multiply those together, you've got 8 different copies of the page cached. But we can serve out of the cache in half a millisecond, whereas hitting the PAL to render the page is 200, 300 milliseconds. So that's how we try and make our site as cacheable as possible, and we can use less servers because we can deliver as much content as we can out of cache. One of the problems we've got at the minute is we don't really know what's going on. Our monitoring system is Zeus, and we basically log data as SNMP style key performance indicators into Zeus, and we have Apache error logs, and that's pretty much all the monitoring we have at the minute. So if your application errors and you get a 500, we won't know about it for 5 minutes, and then all we'll get is a little blip on a graph, and it's really not very suitable. So what we really want is so we do get that information per application. So we see there were 20 error 500s on iPlayer in the last 5 minutes, but we don't get much more than that. And a lot of the applications can log as much data as they like, so they kind of number of service calls they make, how long it took. But the frequency thing is really killing us. So what are we doing to improve this? So we're still using the Apache logs. We looked at using, I forget, there's an internal PHP function that I've forgotten the name of now that allows you to augment extra data into the Apache logs. But you're still limited to a single log line, and it gets very difficult to try and parse that information, and then you have to have a data warehouse to process it. We don't have all that information, so we came up with some other prototypes, and so we thought we'd do this in Varnish because we can get access to low-level stuff using C libraries inside Varnish. So what we've done is we are now implementing per application statistics in Varnish. Varnish out of the box is really designed to sit in front of one website, which technically we are, but you basically get a big blob of data that is cache hits, cache misses, and things like that. And we wanted more granularity on what exactly is happening inside our caching layer. We'd also like to know that if we look at Varnish at the minute, we see we get about a 30% hit rate, which seems really, really low, and we don't know why that is. So we can't really investigate because the Varnish logs are huge and incomprehensible. So we've implemented something we called StatsD, which we've also found has been implemented by other companies like Etsy as well. And ours is very similar, and we're kind of migrating to make it even more similar so they're interchangeable. And what we've done is we do hit, miss, and pass ratios inside Varnish, and we do interquartile ranges, and we do it updating every 10 seconds, which is significantly better than the 5 minutes we get out of Xenos. So this is a quick look at part of our Varnish VCL for the BBC. So we drop into C. The curly bracket with the C just says I'm now dropping out of VCL language and into C. We include a whole load of standard C libraries. We set up a port to our to a socket, which is a FIFO on disk. And then we basically just have 3 functions. We have one function called get file descriptor. We have one that says increase a counter, and another that says close the file descriptor. The get file descriptor, so Varnish is multi-threaded. We have about 4,000 or 6,000 threads running inside Varnish. So we have to make sure that we don't step on any other threads' toes while we're doing this. So we really don't care too much if we throw data away. So I won't go through this particularly, but all it's doing is opening a socket to a FIFO on disk, and then it's returning a status to say, yeah, here's your FIFO. When we increase the counter, what we do is we pass a blob of text in with a bit on the front that says, this is the application, this is what we're doing. I'll just skip this really. If you want this, the slides are on GitHub, but you can have a look at the code and have a look at our implementation. But this is really what we do. So we have in VCL deliver, which is when we're pushing content back to the client. If we, what we've done in our PHP layer is the PHP layer sends back to Varnish an extra header, which we called X web app, that identifies the page that is being served. So in this case, it would be iPlayer or homepage or CBBC or something like that, so that we know exactly which web application was being served out of Varnish. And then we just pass into our increase counter that this was a cache pass, or this was a, so we maintain more accurate, well, technically more accurate, I guess, whatever, hit, miss, and pass ratios. The reason that we do this is, so Varnish will just give you a hit and miss ratio. We want to know why things missed. And we also want to know why things passed. I don't think I covered this terminology. A pass in Varnish language is something that would have been a hit, but for some rule in your logic that tells you how to manage your requests, you decided not to serve it as a hit, and you actually went back to the back end and got the data. Normally that's because the back end said that this page is not cacheable, so I want you to always go fetch it. Or it could be because the server issued a set cookie because somebody changed their user preferences or logged in or something like that. So we record all of these reasons and we push them into our stats so that we can actually see that the reason that CBBC is not caching well in Varnish is because they keep issuing set cookies on every page request or something like that, which we have found before. Then also we do, then we push that into our stats monitoring system. Which one's this? Oh, the PCL hit. This was just to cover all the bases. So this is what happens when we actually do get a hit. We just push in, say, yeah, we got a hit on this application, and we also got a hit in total for Varnish. Right. So now we're generating all this data. What are we doing with it? So it's all very well to have this stuff generated, but we've got to put it somewhere. We've got to find out what exactly is happening. So the other thing we've implemented is XHProf, which is the Facebook's kind of slimmed down cache grind xdebug type output, but it is designed to be run into in production. And so we are actually doing that. We're sampling 1 in every 10,000 requests at the minute, because we only have a kind of development environment set up for handling the storage of this at the minute. Once we've sampled it and we've seen how much data we're getting and how easy it is to process, we may scale that up. I mean, ideally, we'd like to process every single request, but that may probably not be practical. We're using the XHProf GUI, which is the Paul Reinheimer clone of it on GitHub. We've made some amendments to it that we're going to be pushing back. I'll just give you a quick demo of that because I think I've got it up already. So this is on our test environment. Ooh, that looks nice. Oh, there we go. So this is actually running on our test environment. It really doesn't look very pretty. But if we look down here, so you see we get some really huge URLs and things in here. But if we look at, say, iPlayer, so this is all the iPlayer requests, and we can see the CPU time, and these are all individual processes and how much CPU and how much memory was taken. And we can drill into here with any luck. Pick a profile. And we then can go down and look at an individual request. We get a nice pretty cool graph, which looks a bit better if your screen resolution's higher. We can even drill down and see BBC Autoloader was called 139 times. We get which functions we're calling it. So if you're used to looking at cache grind outputs or things like that, it's pretty much the same sort of thing, but in a web interface. So we're storing that at the minute in a MySQL database. We're looking at other alternatives for storing that. We're aggregating this across all of the BBC platforms. We don't actually store this on disk and collect it off the servers. We use something called Teleport D. So we have a FIFO pipe on disk. So we're not actually touching the disk at all with this. Teleport D is a transport mechanism. It talks to a FIFO on the disk. Any data you push in, it sticks out over a TCP connection. If there's nothing listening at the other end, it just drops it. But if there is something, so you have a FIFO on your destination, and you have a client listening, and it just pulls stuff out. We send all of this information to something we call internally the Schrödinger logs, which is basically, if nobody's there to look at it, it doesn't happen. Because, like I said, Teleport D, if nothing's listening, just drops it. So we then have our server that is running this, the XHProf GUI, has a Python script that sits and listens to the pipe. We've had to come across some hurdles because in PHP, well, in fact, any language, pushing data to a pipe on disk, or in fact, any file descriptor, if you do a fwrite, it doesn't necessarily write the whole content in one go. Depending on your operating system, you may get 64 bytes or you may get 512 bytes or whatever. So we have to find a decent way to flush that to disk, which is well, that's pretty simple. The problem we had was actually decoding it at the other end, because we're multiplexing streams from all of our 40 boxes, and the logging portal combines all those FIFOs from all the different servers into one port. So we don't have to make 40 connections to listen to the logs. We only make one connection, but it means that they're all interspliced with each other. So I'll talk very briefly on how we do that. Sorry, I haven't actually done this presentation before, so I apologise if things are a little bit garbled and out of order. At the minute, we generate the profile ID, which is the unique reference to a single trace in the PHP layer, and we pass that into our data transport to identify this stream, and we pass it over the teleport D system we were talking about. Because XHProf generates a JSON object, it can be quite large. If you saw the call trace information, all that timing information, memory deltas, who called what, when, how many times, all that is encoded in a JSON object. It tends to be getting on for a meg of gzipped JSON. So yeah, it's not tiny. That's the other reason that we don't hit disk with it, because we don't want to incur the latency on our front ends. We just stick it straight out over the TCP connection. So we gzip it, and then we add a data framing. So we generate the profile ID. We then send a line that says, this is the profile ID, this is how much data I'm going to send you. We send that straight off. Then after that, we chunk up all the data. We chunk up all the data on new lines, and then we insert on the front of the new line, we insert the profile ID, or I think it's the profile ID, then a bar, and then we send the rest of the data. Then the script at the other end picks out the profile ID, says, oh, I'm expecting 54 bytes of data, 54 kilobytes of data. Then it basically assigns that into a bucket, and then it demultiplexes all the different lines as they come in, looks at the profile IDs, strips off the data framing header, and appends it all to the content. Once we've got a full frame, as in we've got our 56 kilobytes of data or whatever we're expecting, we then ungzip it and then JSON decode it, and then we write it into whatever system we're going to store it on. We write as much as we can, and we just throw away any errors, because at the end of the day, it's profiling information. We're sampling 1 in 10,000 or whatever. If we miss one, it really doesn't matter. If there's any errors in the gzipping, we just don't care. We don't want to investigate errors, particularly unless it all stops completely. So we pretty much throw away everything. This is the amendment we made onto the end of the PHP XHProf stuff. So we open our pipe, and if we do log an error, but we just say couldn't open the pipe. It just gives us something to look at. We say that we are going to not block, so we don't want to cause any blocking on here. We JSON encode our data, we gzip that, we work out the length of it, and then we write the size of the data that we've got, and then we do, so once we've gzipped all our data, there's going to be carriage returns in there because just random garbage of things being translated into gzip. So whenever we find a new line, we prefix it with the size of the profile, and then we flush it out the buffer, and then once we're done, and if we close the socket, and if anything goes wrong, we do actually log an error. I didn't think we did, but there you go. So that's how we handle our XHProf, and we get that into our XHProf GUI. We thought we could do better than this, because XHProf will give you, typically for most of our applications, it will show you that you made a request to curl 3 times in your page, and you spent 200 milliseconds in curl. And we didn't know we wanted to find out what was really happening. So we came across something called the HTTP archive format, which if you've ever used Firebug on Firefox, is the waterfall diagram you get that shows you your CSS and JavaScript loading and how long it took to download an image and how many things were done in parallel, all that kind of information. So that is all encapsulated in a format called HTTP archive. So as we already had this transport available to us for Teleport D, we thought we'd see what we could do with this. And what we generate is, we've extended, so we're using Zend Framework, and we have our PAL layer on top of this, and we have a BBC HTTP client that extends the Zend HTTP client. So we hooked in some metrics in there, and we basically start a micro timer before we make a request. And then when the request is finished, we stop the micro timer. We also take a copy of the curl handle and pass that into our performance monitoring class. And then that generates an HTTP archive format file for what is happening in, we also did the same for Zend cache core. So we now get all the metrics for what's happening in memcache. Rather than post this data into a MySQL database, we're actually posting this into our key value store, which is actually CouchDB, but with a Mickey Mouse front end on it, that basically only allows you to post and fetch and delete. The reason we're doing this is that we'd like to take advantage of CouchDB views to actually get an idea of what is happening with our requests and who the most expensive requests are. So this is a very, very sport with a cache buster on the end. So this is a very quick view of the kind of output that we get from our, this is a single page request. So they were making a call to memcache that did an increment on a counter that took 0 milliseconds. The next one down is a get. So they were actually fetching data. You can't quite see it, but it was making a call to api.int.bbc, and the status on there is 304 memcache hit, and it took 6 milliseconds. And then they did actually fetching something from memcache as well, which took another 5 milliseconds. And if we have a look at that expanded, the get request would have been a curl request, but because of the way we've extended the Zend HTTP client, we've stuck some wrappers in there to enable our client SSL connections, because I don't think Zend does that, or certainly the version of Zend with it running doesn't do that by default. So we've also augmented it so that by default it will look up the data in memcache before it actually makes the curl request. So if somebody on their PHP application is making lots of requests to the same curl resource, when it receives the response, if the response is cacheable, it will take a hash of the URL and it will push it into memcache. So before we make a curl request, we go check memcache to see if there's a cache copy in there, and we return that, and we save ourselves about 100 milliseconds normally. So this was a cached response, but we can see that we actually got the response and request headers that were actually sent, or were sent originally to the back-end service. So you can see that max age 60. It was cached for 60 seconds. There was an E tag in there and all that kind of stuff. Right. So I said we were extending Zend HTTP client. I think I've already basically mentioned all of that. And I've probably already mentioned this one as well. Yeah, so we already extended BBC Cache Core as well to implement our own hashing algorithm. So we've now just added on performance information. We can also get information on APC, because APC in Zend is actually an implementation of Zend Cache Core. However, we found that they all take 0 milliseconds because it's an in-memory swap, and you just end up with 60 or 70 of them in your page. It's really not very useful. So I thought I had some. Okay. So that was a brief look under the hood of what we're doing inside the BBC. what we're currently doing is, we're trying to data mine all this data that we're starting to get. So the idea is that now that we are aggregating across the whole of the BBC, who is making service calls to what service endpoints, how long they're cacheable for, how big the data was, how long it took to deliver the content. We can now start to rank all the applications in the BBC, all these 360 applications, and we can rank them by frequency, so like iPlayer and Homepage are hit lots, but things like the performing arts web application page is probably hit once a week, if that. And we can rank them, and we can say, your page is very expensive for us to serve on a platform. And we're trying to come up with some kind of metrics that we can kind of say the average cost to deliver a page on the BBC, and then we can equate which are the good performing and the bad performing sites. We can also look at who is making calls to particular API endpoints, what frequency, whether they're caching them correctly. We've already spotted some sites that are bypassing the BBC HTTP call to hit memcache first, and they're actually going direct every time, and it's just one line change to remove a switch when they make their request or set their HTTP client up to actually say go to memcache first, and that would probably save us hundreds of milliseconds per page request for their application. And basically we're generating a huge shit list that we can go around and we can poke people in the BBC and say, fix your shit. So what's happening next? So at the minute, we're only doing this for the PHP layer. We're now going to start passing the profile ID that is generated to record the profile information. So I didn't mention it. We actually send back to the client a header. We only do this. So on every environment other than live, so on int, test, and stage, you can set a cookie or you can set a header, and you can hit your page and it will force a profile, and then it will send you back in the request to your browser. It will send you a header which is X BBC profile ID, and then it's a blob of data that you can then go and cut and paste, although we're thinking of something like a Grease Monkey script that will then give you a little button at the bottom to say view my trace, and that will take you to the XHProf GUI page, and it will take you to the hard data page so that you can then see that page profile information. We're actually going to pass this information, the X profile ID, onto the service, our Java service layer, because at the minute now we can see we're making 2 calls to our Java service layer, took 200 milliseconds. So what was the Java service layer doing to take 200 milliseconds? So we're going to get the Java service guys to implement the same data format, this HTTP archive. So then we'll be able to see all the way through this page request, did all of this data inside PHP, made these curl requests to Java. What was Java doing? Oh, it was making 10 calls to MySQL. This was a long-running SQL query. All that information, all in the same format. So again, you paste your ID that you get back into your page, or you click your button or whatever, and you will get a whole stack look at what your application was doing and what was taking the time. We're also looking to see if we can actually push this further, and rather than get PHP to force the profile, because we own Varnish, we're going to do it in Varnish, which then means we can probably put some interesting metrics as to what happened in the caching layer. We're also in discussion with our network operations team to see if we can actually get the random select who to profile thing done at the ZXTM layer. So we also see what traffic routing calls were hit in our traffic management server, and then we need to implement an interface to aggregate all of this data together. And that is the end of my talk. Thank you very much for listening.
Yeah, just wondered if you could summarize the things that Varnish gives you that the Zeus traffic manager doesn't.
So basically, it gives you, I guess, I wasn't there when Varnish was introduced, and it's kind of I got handed this as a legacy when I joined the BBC. As it happens, I'm very, very impressed with it. I think the main thing it gives us, we probably could implement most of these things in Zeus, but the thing that it does give us is flexibility to be able to change it ourselves, because otherwise we have to go through hoops with the network operations teams. So this sits as a separate caching layer. The other thing is we can scale it as much as we like. We've got 64 gig boxes, 64 gig of RAM boxes, and our current usage for cache is about 10 gigabytes, so we've got lots of room for expansion in there. I think the Zeuses tend to use most of their... So the other thing we do is we send a header back from Varnish to tell the Zeuses not to cache it, because otherwise they would cache it as well. They are limited on RAM. I think they normally have about 4 gigabytes of RAM available for cache, and most of that is used serving static assets, images, CSS, JavaScript, and I think the general consensus is that they prefer to keep it that way, and the dynamic stuff that is cacheable is by far larger volume of data. They prefer to keep that in a separate caching layer.
Right, a little bit to expand on the question about Zend Framework, bearing in mind the version 2 is coming out at some point.
Sorry, Zend Framework?
2. It's more about Zend Framework 2. Do you make any plans to migrate to Zend Framework 2, or?
So the other problem with running a shared hosting platform with 360 applications, some of which were developed 2 or 3 years ago and haven't been touched since, we had a huge problem getting up to PHP 5.3. It took us 3 attempts, I think, to do it before we actually got it to stick, because of just random crap that was 2.5 years old that nobody had looked at. We did manage to upgrade Zend Framework to the latest, I think it's 1.6 something. We did manage to upgrade, but again, it did take us two attempts before we got that. We tried going to the latest Zend Framework 1. Sorry? Yeah, and that broke so many things. We are committed to, as the frameworks team, we are responsible for Zend and the things that sit on top of Zend, but not the actual websites. So we've actually built a separate. So we have an int test and a stage environment. So integration is where developers commit their stuff and it gets built onto there. Test is when they're happy to test it. Once they're happy, it's ready for release. It goes to stage. Int and test are managed by developers. They can roll and push their products out there as often as they like. Everything stage upwards is managed by the network operations and delivery team, the site operations team. So that's when it becomes more production ready. So we've built a separate environment, we called it the engineering environment, which is actually a model of the live environment, just so that we can test new releases of Apache, new releases of PHP and Zend Framework. And all we can do is roll it, push it out, see what breaks, and then just log tickets against iPlayer and BBC homepage and say, fix your stuff, and then we'll try again. But that takes a long time, because their releases don't necessarily tie up with our timescales. So yeah, we're committed to try and doing it because we need to keep up to date, but I'm not sure whether we'll be able to in the short term. And we'll also be coming up to the Olympics, and there'll be a freeze on major impact changing on the infrastructure. So hopefully by the end of the year maybe, but I'm not holding my breath. Oh, sorry, yeah.
What's your approach to cache invalidation?
We don't have a cache invalidation mechanism with Varnish. So it's up to the individual application owners to set their cache message and appropriate e-tag headers and things like that. We do Varnish grace periods. So we have stale while revalidate, which reduces the load dramatically, because you only, the first request that has reached the max age hits the back end, everybody else is served stale data until it refreshes. But we don't have a cache invalidation mechanism. We could implement one, we haven't had the need for it just yet.
We've got time for one more if...
Hello? Hello? Hi. You've obviously done an awful lot of research into performance and caching and that kind of thing. If you were talking to an organisation that's got pretty high traffic on their site and they've done nothing so far, so it's a lamp stack and they've got no caching at all, and you could recommend one thing for them to do, what would it be?
Well, actually, yeah, there is something to be said for just sticking Varnish in front of a site. Just out the box, generally, you get, well, as long as you're not setting cache control private or setting cookies on every request or something stupid like that, you probably get some benefit out of it. What caused us a lot of problems was our international domestic switch for the header and footer, and it's taken us almost a year to solve that sufficiently that we're happy with it and can we're now actually in the process of sticking Varnish in front of every single BBC site. So we will be using Varnish for everything very shortly. But we've had to do a lot of proving. But yeah, I mean, just make sure that you understand how caches work and that you don't make your page uncacheable by setting cookies or setting, yeah, disable PHP sessions is probably a good one as well.
Okay, well, okay, maybe just one more.
Are your servers virtualized, or do you run
no, we're all
machines?
Commodity servers. We don't do virtualized. We have some of our testing environments that are not our standard testing environments. So we have something we call incubators, which are for like test projects. They're virtualized. We run Red Hat, and we've been looking at the Red Hat virtualization system. I mean, I think we will eventually, but for the time being, we're all running on commodity servers for everything in our own data centers.
Excellent. Thanks again. And guys, we've got lunch outside, so yeah.
Thank you.